All right, so some of you asked for PowerPoints, so here we go. We're going to be, it should say Unit 10, it shouldn't say Unit 9, so I'm going to escape right here and change it. So we're also going to be using your textbook, so hopefully you brought your textbook home. If not, don't sweat it, okay? There should be plenty of information on videos and stuff that I offer. So what are the objectives in this unit? Well, you're going to define the properties of acids and bases. And then just for this short part, you're going to compare and contrast acids and bases and define as they're defined by theory. So there's two theories. There's Arrhenius and there's Brownstein-Lowry, which Regents people don't think you could handle that. So they call it the alternative method. But your college professor will want you to know that. So let's go on. Here's some of the definitions. So Arrhenius, all you really need to know if it has an H to start with, and it's usually an acid, right? HCl, etc. H2SO4, right? What is it? Gianni was a chemist. Gianni is no more. What he thought was H2O was H2SO4, or it has an OH at the end of it. Okay. Now this OH is going to run into problems when we get into organics, but right now, if it has an OH, a polyatomic OH at the end of it, it is a base. So an acid, according to Arrhenius, has an H plus, and a base would have an OH. Brownstein-Lowry is it's either a H plus donor or an H plus acceptor. Then there's another pair called Lewis that we don't really get into, which is an electron pair acceptor and electron pair donor. And I'll give you a way to remember Brownstein-Lowry. It would be brought to you by Michael Jackson in the future. Hold on. All right, so what do we remember that light bulb experiment that we did? Okay, well, acids do the same thing. Recall that an electrolyte, right? Electrolyte or lytic, things get broken apart, and then you have electricity, is a substance that dissolves in water and forms a solution that conducts electricity. So water can conduct electricity. It's the stuff in water that's conducting electricity. But if we put acid in water too, the same thing's going to happen, right? So it's the ability to conduct an electrical current due to the presence of ions. Now you learn that ionic compounds dissolve in water, not covalent, but you're going to learn that acids, which are covalent, can be broken into ions, and therefore they can conduct electricity. So now instead of just saying ionic, we add polar covalent compounds. So let's move on. So how do you know if a chemical is an acid? Well, besides just like pouring it on you, which isn't a good thing, right? You don't want to do that. So hopefully you just look at it, read the name, and if it usually starts with hydrogen, odds are pretty good it's an acid. So you have HCl, H2SO4, HNO3, etc., but not water. Okay, water is not an acid. Which ones don't start with water? Well, you go to your handy dandy reference table, and they'll show you which ones don't. So here we go. Table K or cable T. So here is really where you have to go for it. The only one that's really tricky is the last one, ethanoic acid, better known as acetic acid. It's really popular in organic. It's an organic acid. But if you look down below, the pointers don't work, I don't believe, when I'm filming. But the last one says H, right? C2H3O2. And if you go to your polyatomic ions and you look up C2H3O2, you'll find that acetate is a polyatomic ion. It's got an H attached to it. Sometimes they write it like ka-chew, like a sneeze, and we'll get into that later when we get into organics. If you look at CO2, carbon dioxide, is an acid. However, it's when it's in aqueous solution. So Coca-Cola is an acid, right? It's those bubbles. Champagne is acidic. One of the things that we have to worry about isn't necessarily global warming. It's the fact that CO2 is being absorbed in large numbers, large amounts, I should say, by our oceans. So our oceans are slowly turning acidic. Think about that. More about that later. Okay. So here's Arrhenius. He's a handsome gentleman. People tell me he was a genius. So he's the person who started the first theory on acids. It's called the Arrhenius Theory. So how do we follow his definition for acids and bases? Well, if you look, you have HCl, which is an acid, and then you have the H, which is ionic, right? Not ionic, I'm sorry, but it's an ion. Chlorine is an ion. So an H plus will give you an acid. When the H plus combines with water, you have H3O. So H plus H2O gives you H3O. It's called hydronium. When you watch the Mark Rosengarten video, they're going to talk about coordinate covalent bonds. This actually comes up in there. So oxygen has two double paired of electrons on the outside of it, if you remember. And when the H comes over, it forms a coordinate covalent bond. That is considered hydronium. That's what the H in pH stands for. It stands for the power of hydronium or the power of hydrogen. So here's what I'm talking about with coordinate covalent bonds. So if you look up top in the middle, there's water. Remember, it's polar. It's a bent molecule from our molecule model days. And then the hydrogen up top will just land on it. There's that creepy guy that always asks for cigarettes. Remember him? Just kind of snuggles in there. So he'll come in and form a coordinate covalent bond, and then that'll be a hydronium ion. So it's covalent and it's coordinate covalent. So here are some of the rules. Acids have a pH less than 7. So anything less than 7, 6, 5, 4, 3, 2, 1, 0. Look at lemon juice. Pretty acidic. It's crazy. All right. So strong acids, they're aqueous solutions of acids that conduct electricity. When you look at your reference table, the strongest acids are on top, the weakest acids are on the bottom. So acids are electrolytes. They react or eat away. They oxidize metals. So H2 on table J to form hydrogen gas. So let's take a look at table J. Okay, here it is. Notice that hydrogen with 2 asterisks next to it. I sound like Joe Biden. Asterisks next to it. Everything above it, right? So it'll react with anything below, it will not. So copper, silver, and gold, which is why you give your loved one expensive jewelry. So it does not oxidize. So rule number 2, the most active metals are near the top. We know that the arrow shows the activity decreases as it goes down. Metals above hydrogen are more active than hydrogen, and they react. So therefore, HCl will produce hydrogen gas. Remember, that's a single replacement reaction that takes place. So the Ca will knock out the H, forming calcium chlorate, and then you'll have your hydrogen gas will be given off. Your acid, there's your active metal. There's a salt that's formed, and there's your gas. So that's a single replacement reaction. Acids affect indicators. You probably remember a litmus paper. We would get into a whole bunch of indicators in class. We're going to try to do these online. They're kind of tough to do. Blue litmus paper turns red in contact with acid. Red paper stays red. Here's one that we use a lot. It's phenolphthalein. It's a colorless in an acid. How do you remember this? Do you think you have to remember this? No. Again, here's your reference table. I'm going to probably do a video on this alone. But if you look at it right here, let's just look at the first one, methyl orange. When it's in this range, it's going to change color, okay? So before 3.2, it's going to be red. 4.4 and higher, it's going to be yellow. When it's in the middle range, it's going to be red-yellow. Same thing with all of these, and we'll get into more of that later. So there's phenolphthalein. That's the one that we would use if we did a lab. I might have you guys do a lab on, it's called titration next week, but not this week. No lab this week. Acids and bases, acids will react with bases to form a salt and a water, okay? We call this neutralization because if you take an acid and mix it with a base, you get salt water, right? So if you jump into the ocean, nothing's going to happen to you unless you don't know how to swim, and it's going to be balanced. So here we have hydrochloride, and then we have sodium hydroxide. Very strong acid, very strong base. When we put them together, it is a double replacement reaction. Remember, I said something like the next unit is if trying to think if double replacement reactions and something else had a baby, it would be acids and bases. Well, here you have it. Just think of H2O as HOH, right? And then you can really see how the double replacement reaction really takes place. Also, they're soury, right? So that's why Sour Patch Kids taste the way that they do. Also, lemons and limes, right? Highly acidic. Citric acid is very, very acidic. So I ask a question, why are lemons more soury than oranges? Why are grapefruits more sour than oranges? I don't think soury is a word. I was going to make another Joe Biden joke, but I won't. Acids react with bases to form a salt and water. Okay, so that's rule number 4. And they react with indicators. Talked about that. So I don't know why this is showing up again. I know why. I'm going backwards. Sorry, guys. There's table K. All right. So most you guys are probably going, this guy's out of his mind. Should I start over again? Nah. So strongest acids on top, weakest acids on the bottom. Here's some examples of acid. Hydrochloric acid, super, super strong. So it is for pickling steel. So it's used to purify magnesium from salt water. It's part of your gastric juices, so there's a biological connection. So you have HCl in your stomach. So when people like pour Coca-Cola, like you'll watch a video on YouTube and like, yo, don't drink Coke. And they'll pour Coke on a car and the acid, because the CO2 will eat away the paint. And they're like, oh, just imagine what it's doing in your stomach. Well, your stomach actually laughs at Coca-Cola. It's just kind of a joke. So your pH in your stomach is like a 1. Then there's nitric acid, which is in HNO3. So here are some of the uses for that. Then there's sulfuric acid. This is the highest volume of any chemical sold in the United States. It's used for the production of paper, so we use a lot of it, especially here in Glens Falls. It's also used in fertilizer. So obviously we use a lot of it up here as well. It's used in petroleum, which pretty much everything is made out of petroleum because that's what plastics are made of. I want you to notice something with the names. So now I know I'm going backwards. Notice where it says hydrochloric acid, right? HCl. Cl is an element. Nitric acid, HNO3. What is NO3? It's not an element. What is it? And H2SO4 is sulfuric acid. So those when we start getting into names. And here's another one, phosphoric acid. What is PNO3? That's in a lot of our sodas. Right? So besides the carbonated water, you have this flavoring agent. Gives it a little tart taste. Also used in fertilizer. Not a lot of use for it in the laboratory, however. And then my favorite acid, vinegar, right? So a fancy name for acetic acid or ethanoic acid. And when we take organic chemistry, you'll understand why we call it ethanoic acid, not just acetic acid. But in this unit, when it's HCO2, H3, it's HC2H3O2, you'll notice that C2H3O2 is a polyatomic, okay? We just write it differently in organic chemistry just to confuse you. Here are some of the effects of acid rain. That's George Washington before acid rain. This is actually taking place in Washington Square in Manhattan. So if you go to NYU or ever visit a friend in NYU or just go to Washington Square in Manhattan, it's actually a fun place. Marble is calcium carbonate. So this is what I was talking about with CO2 and water, why it's not a good thing. This is what our first president looks like today. Okay. Not good. So acid will break down certain things like calcium carbonate. Why is that not a good thing? Well, a lot of the oxygen producing organisms in the ocean are actually made up of calcium carbonate. So if you remember, you might have done this experiment with Miss Husky, or if you want to do it at home just for fun, just take an egg, put it in vinegar, wait a couple of days, you'll start seeing it reacting right away. It'll start to bubble, and then all of a sudden, no shell. All right. Now, if I'm a oxygen producing organism who has even a thinner shell than an egg, a chicken egg, and my ocean becomes acidic, we might not have to worry about the planet warming because we'll go outside and take a deep breath, and there might not be enough oxygen there. All right. Although we do have a lot of oxygen, we can pretty much cut down all the rainforest trees and we'll still have enough oxygen. But it will eventually stop being recycled in the carbon cycle. But that's for another place. So we're going to end here. We're going to do bases tomorrow. I hope all this was helpful. Sorry I went backwards there for a little bit. If anybody got offended by my Joe Biden jokes, I do make fun of President Trump as well. All right. Have a good day. See you tomorrow.